Hey everyone! So today we're going to peek behind the curtain of one of the most fundamental tools in all of data science, that simple line of best fit. We're going to unpack the surprisingly elegant math behind what's called ordinary least squares regression, and it all kicks off with a question that I'm pretty sure you've asked yourself at some point in a math class.
Yeah, I'm pretty sure we've all been there, right? Staring at a board full of equations and wondering, seriously, when is this ever going to be useful? Well, today's the day. It turns out this stuff is the actual engine that drives a massive amount of quantitative research, and we're about to see exactly how it works. So here's the core problem we're trying to solve. Just picture a scatter plot in your head, a cloud of data points. You can almost eyeball it, right? You can kind of see where a line should go. But how do we find the one single line that is mathematically, provably the absolute best fit? And what does best even mean in this context? Okay, so this is where we get a really precise definition. In statistics, best means the line that makes the total amount of error as small as it can possibly be. And we measure that error by looking at the vertical distance from each individual point down to our line. We square that distance, and then we add all of those squared distances up. So our mission, should we choose to accept it, is to find the one line that makes that grand total, the sum of the squared errors, as tiny as possible. So let's dive in. This brings us to the first part of our story, formally setting up this quest for the best fit line.
All right, let's start simple. Let's say we have just one independent variable. We'll call it x, and we're trying to use it to predict some dependent variable, y. The equation for any straight line is y equals b0 plus b1 times x. Now b0, that's our intercept. Its job is to tell us where the line crosses the vertical y-axis. And b1 is our slope. It controls how steep the line is. The whole game is to find the perfect numbers for b0 and b1. And that little e at the end, that's the error. It's just the leftover bit, the distance from an actual data point to the line we've drawn. So to put it all together in mathematical terms, here's our goal. We need to hunt for the specific values of our intercept, b0, and our slope, b1, that make the sum of all those little squared errors an absolute minimum. We're looking for that one perfect combination.
So how on earth do we actually find that perfect combination? I mean, we can't just guess and check forever. Well, it turns out the hero of this story is differential calculus. And don't worry, I promise this is going to make sense. Let's just break this down for a second. The word derivative can sound intimidating, but all it really is a tool that tells you the slope of a line or a curve at one specific single point. That's it. Is the curve going up? Is it going down? And how fast? The derivative tells you. Okay, and this is the key insight. This is the whole trick. Imagine our sum of squared errors function as a giant bowl or a valley. The lowest possible point in that valley, the bottom, is the one spot where the ground is perfectly flat, where the slope is 0. So if we can use a derivative to find the exact spot where the slope of our error function is 0, then we've found the bottom. We've found our minimum error. So this gives us a crystal clear 3-step game plan. First, we're going to write out our big error equation. Second, we're going to use those derivatives to find the flat spot at the bottom of the valley. And third, we're just going to solve for the b0 and b1 that get us to that exact spot. Okay, game plan is set. Let's put it into action and solve this for our simple case with just one x variable. Here we go, step 1. All we've done here is replace that little error term e with what it actually stands for, which is the real y value minus the y value our line predicts. And now you can see this whole equation is just a function of the two things we're trying to find, b0 and b1. Now for step 2. Think about it. Our error valley has two dimensions, right? The error changes when we wiggle the intercept, b0, and it also changes when we wiggle the slope, b1. We need to find the spot that's at the bottom in both directions at the same time. That's what a partial derivative does. We take one with respect to b0 and one with respect to b1, and we set them both equal to 0. This is how we find that single point that's at the bottom of the valley from all directions. And then, step 3. This is the moment of truth. We now have two equations and two unknowns. We just have to do a bit of algebra, solve them together, and what pops out are the exact perfect formulas for our best fit slope and intercept. We've done it. We've found the bottom of the valley. Okay, so that works perfectly for a simple case. But what about the real world, where you might have 5, 10, or even 100 variables all trying to predict an outcome? Things would get messy fast. This is where the whole thing gets, well, Really elegant.
And this, my friends, is where matrix algebra becomes our superpower. It's like an incredibly powerful shorthand. That simple equation we started with on the left scales up perfectly into the compact and powerful matrix equation you see on the right. Now, capital Y is just a whole column of our outcomes, capital X is a big grid of all our predictor variables, and capital B is a column of all the coefficients we're trying to find.
Now, I know the notation looks a little scarier, but I promise you, the fundamental goal has not changed one bit. We are still just trying to minimize the sum of the squared errors. In the language of matrices, we just happen to write that as E prime E, but the concept, it's exactly the same.
And what you get, after applying the exact same calculus logic as before, taking the derivative, setting it to 0, and solving, is this one, single, incredibly elegant equation. This formula is the magic key. It solves for all of our coefficients, the intercept, and every single slope for every variable, all in one go. It's pretty amazing. Okay, I know that was a lot of symbols and equations, so let's zoom back out for a second. Why does any of this abstract math actually matter in the real world? Look, this isn't just some dusty old proof from a textbook. This derivation is the workhorse behind quantitative research in fields like economics, psychology, sociology, you name it. It's powerful because it guarantees there is one single optimal answer for the best fit line. It's also the conceptual ancestor to many of the much more complex machine learning models we use today. And maybe most importantly, it's just a beautiful example of how really abstract mathematical ideas can give us incredibly powerful concrete tools to make sense of a messy world. And here's the coolest part, the way to tie it all back together. That big, intimidating matrix equation, it's really just a superpowered, generalized version of a much simpler idea. In our simple one-variable case, the formula for the slope is basically the relationship between x and y, what we call the sum of cross products, divided by the variation in x, the sum of squares. That big matrix equation is doing the exact same thing, just in a way that can handle any number of variables you can throw at it. And that really just leaves us with one final thought, doesn't it? Ordinary least squares is just one example of this kind of powerful, almost hidden math that's running just beneath the surface of how we analyze data. It kind of makes you wonder, what other elegant equations are out there, quietly shaping the way we understand our world? Thanks so much for joining me on this one.